Today we're going to be learning about similarity in different shapes, and we'll be taking notes on pages 41 through 42, doing a practice exercise on page 45, and going through some word problems on page 48. So we're going to start today taking a look at an example of similar polygons. We have a rectangle here with a width of 3 inches and a length of 6.5 inches, and another rectangle that's been reduced with a side length of 1.5 inches for its width and 3.25 inches for its length. So this is a great example of similar polygons. In similar polygons, we see that the sides are proportional. So that means that there's a relationship between corresponding sides. So in this case, maybe you notice that our k value, our scale factor, was 1/2, because half of 3 is 1.5, and half of 6.5 is 3.25. What we also notice is that no matter how we change the shape of, whether we dilate it and enlarge it or reduce it, the angles are always the same. So now let's go on and take a look at some symbolic notation and an example. Let me move this up a little bit so you can still see this. Okay, so we have two triangles here. We'll call this triangle A, B, C, and triangle D, E, F. And let's go ahead and show that these triangles are proportional. So this side is 2 inches. This side is 3.5 inches, this side is 6 inches, and then some corresponding sides. This is 12 inches, this side is 7 inches, and lastly, this side is 4 inches. So now that it clearly shows that all the sides are proportional, we can say that triangle ABC is similar, so I make kind of like a curly symbol, to triangle DEF. Now, just like in congruent triangles, the order matters. So take a look what we did. Triangle ABC, so it's going in this order, starting at point A. In this case, triangle DEF. Now, when I write that, that means that AB has a relationship to DE. Let's check. AB to DE. Yes, DE is twice AB. Same with this. BC and EF should have a relationship. 3.5 and 7. 7 is twice BC. And the same here, AC is half of DF, or DF is twice C. So when I look at these triangle relationships, when I write in symbolic notation, I should clearly be able to see which sides are proportional. So using the example that we just created, let's write some proportionality statements. So for example, just like we said that AB had a relationship with a DE, we can write that AB over DE has a relationship in the same way that BC had a relationship to EF. So BC and EF. And then our last one is AC and DF. AC and DF. Now, what I want you to note is that I compared the smaller triangle to the larger triangle. So I always went in that order: small triangle to big triangle, small triangle to big triangle, small triangle to big triangle. And I'm also choosing corresponding sides to relate to each other. So AB and ED, BC and EF, and AC and DF. Now I'm going to use these proportionality statements to find out more information about each of these triangles if needed. Now for the scale factor, we're going to take a look at this website. So here's what it says. I want you to go ahead and copy what's written here in this box. So let's read it together. Let me go ahead and zoom in for you so you can see it a little bit better. It says that the scale factor is a ratio of any two corresponding lengths in two similar geometric figures. We'll take a look at this note in a moment, but go ahead and write that again. The scale factor is the ratio of any two corresponding lengths in two similar geometric figures. Now their note is that the ratio of areas to two similar figures is the square of the scale factor. That's something we noted last class in the dilations task number 2. And this is something new, or maybe something that you heard last year, that the ratio of the volumes is the cube of the scale factor. So that's just something to keep in your back pocket that we may be using later. So go ahead and turn the page and let's take a look at this example. They ask, are the triangles similar? So if the triangles are similar, I know that the sides, the corresponding sides, should be proportional. So let's see if they are actually in proportion. So I see 12 over 4. I'm looking at 12 and 4. How about 10.5? What side corresponds to that? Okay, 10.5 corresponds to 3.5. Okay, so 3.5. And then my last corresponding side would be 15 and 10, or corresponding sides would be 15 and 10. The question here, and the way this is written says they are equal, but my question really is, are all of these ratios congruent? Are they all equivalent? So let's go ahead and simplify and see if that is the case. Now, if I simplify this fraction, you guys know I would get 3 over 1. Okay, and if I simplify this fraction, I'll go ahead and be your calculator. 10.5 divided by 3.5 actually also makes 3 over 1. So far, so good. Now, that equality is true. Last one. If I take 15 over 10 and simplify it, let's simplify by 5 over 5, I would get 3 over 2. Now, 3 over 2 is not equal to the other ratios, in this case meaning that triangle LMN is not similar to triangle PQR. Let's go ahead and take a look at example 2. Example 2 says, you have a photo 4 inches wide and 6 inches long that you want to reduce to fit in a frame that is 1.5 inches wide. How long will this photo be? So I have a rectangle, a picture, that's 4 inches wide and 6 inches long. And I'm going to reduce it to an even smaller picture where the new width is 1.5 inches. And they're asking, what would the new width be? Well, these rectangles, just because we are reducing them, means we're dilating them, and a dilation makes similar rectangles. So that means that I can say that there's a relationship, a proportional relationship between these sides. That means that 6 has a relationship with x, 6 has a relationship with x, and the same way that 4 has a relationship with 1.5. 4 over 1.5. Now, our proportionality statement says these ratios, these fractions, should be equal. So I can go ahead and solve. I would get 4 times x equals 9. And then if you divide by 4 on both sides, I'm your calculator, you would get 2.25. And they're talking about inches here, so inches. That means my new width would be 2.25 inches. Now for our next example. Example 3 asks, are the triangles similar? And if they are, write a similarity statement for the triangles. Also, write proportionality statements for the sides, and identify congruent angles, identify the similarity ratio. It's a lot of stuff we got to do. So let's focus on this triangle. First, they ask, are the triangles similar? Let's check the relationship between all the corresponding sides and see if they truly are proportional. So I'm going to see 20. 20 corresponds with 15. How about 16? 16 corresponds with 12. And our last pair of sides is 24 and 18. Now remember, we don't know if these are equal yet, so we're going to simplify these fractions to see if they truly are congruent. So if I simplify 20 over 15 dividing by 5, I would get 4 over 3. If I simplify my second fraction and divide by 4, I would get 4 over 3. Okay, so far so good. Those are equal. And then 24 over 18, if I divide by 6, I would get 4 over 3. Well, that makes me really happy. Okay, the sides really are proportional. If the sides are proportional, then I know that these two triangles are similar. So let's go ahead and write a similarity statement to show that the triangles are congruent. So that means that triangle ABC is similar to triangle, okay, let's look at our order, ABC. So DEF. DEF. Okay, so those triangles are similar. Now they ask me to write a proportionality statement. Okay, so that means, well, let's really take a look at what we wrote here. Instead of writing the measurements, let's name the sides. 20 is AB. So that was AB, and we compared it to DE. Then we looked at 16 and 12, or AC and DF. AC and DF. And lastly, we looked at BC and EF. BC and EF. Okay, those are my proportionality statements. Okay, and then they want me to identify the congruent angles. Okay, well, angle A must be congruent to angle D. Angle B must be congruent to angle E. And angle C must be congruent to angle F. Those are our corresponding angles. And as we know, if two triangles are similar, they have congruent angles and proportional sides, as we showed here, right there. The last thing they ask us to do is to identify a similarity ratio, or they're asking, what's K? Well, believe it or not, we actually already found K. K is the ratio that you can use to find each of the sides. The proportion that we reduced when we were looking at, when we were asking ourselves, are these sides proportional? Now, these are all equivalent fractions, and when we reduce all of these equivalent fractions, each time, no matter how big or how small, we came to the same ratio. That's our similarity ratio. So I'm just going to write that this is what my scale factor is. It's K. Last but certainly not least, we want to take a look at example 4. Example 4 tells us that you have a model boxcar that has a length of 7 inches and a height of 2 inches. So let's go ahead and draw that. We've got some sort of a car. And we'll say that the length is 7 inches and the height is 2 inches. And they have an actual car, so that's, well, this is just a diagram. That's obviously not an actual car. That's 50 feet long, and they want to know what's the height. Well, okay, so it's 50 feet long, so they have enlarged it. That is a dilation, and when you do a dilation, you're creating similar figures. So we have similar figures here. That means that my sides are proportional, so 7 has a relationship to 50, in the same way that 2 has a relationship with x. That means we can set up a proportion. So that means 7 has a relationship with 50 in the same way that 2 has a relationship with x. But wait, Mrs. Martinez, you say, this is in feet and this is in inches. That's right. Okay, in order for this to work, our units have to be the same. So we can make a choice either to convert 7 into feet or 50 into inches. And in this case, I would rather turn 50 into inches. So let's see what we get. I know there are 12 inches in every foot, so that means I have a lot of inches here. So that means that I've got actually 12 inches in every foot. That's 600 inches in this case, would be equal to 2 over x. Now if I do my math, I'm going to have to change here to a white pen here. If I do my math, I'll get 7 times x equals 1,200. Where'd that 1,200 come from? That's 600 times 2, and my 7x came from 7 times x. If I divide by 7 on both sides, and I'll be your calculator again, you're not going to like this, guys. You get x equals 171.428571 inches. It's not a beautiful number. You're okay. Oh, okay, what if I change this into feet? How many feet is that? Oh, well, let's divide that by 12. I'll be your calculator again. If you divide by 12, you could say, oh, that's 14.285712 feet. Still not pretty awesome. Now, if you were really building a boxcar, there's no ruler that would actually take this out to 0.285712 feet. It's not really realistic. Let's just round to the nearest tenth here. So let's just go ahead and we'll say that x is approximately 14.3 feet. So I'm rounding to the nearest tenth. So I'll say that the height of our real boxcar is about 14.3 feet, which is pretty tall.